Okay, this is a continuation of 2.2. Last time we ended with an exercise, which was to take the function 1 over x minus 1 and to find its graph, where we're going to label and find what are called the vertical and horizontal asymptotes. Okay, and what I'm going to do is I'm going to do this, before I do that actually, notice that the domain of f, it's everything except where the denominator is 0, so it's pretty much the set of x where x is not 1, right? So in interval notation, that's negative infinity to 1 as well as 1 to positive infinity. And what's going to happen is actually the vertical asymptote, well, VA for short, vertical asymptote, is going to be exactly the line x equals 1, which is where the function does not exist, where the function does not exist. And does not exist is going to be something we see often. I'm going to shorthand it for DNE, does not exist. And we'll see what happens with the horizontal asymptote. But the vertical asymptotes for these types of problems, most of the time, not all the time, but most of the time, there will be simply where the denominator is 0, aka where you're not allowed the denominator, or whatever points you remove from the domain because of the denominator condition, those are where your asymptotes live. So this again is where the denominator is equal to 0. That's where you'll have your vertical asymptotes. Okay, let's plug in some points here before we actually do the graph. And what we'll do is, we'll plug in just a few here. So let's plug in 2, 3, 4, 0, negative 1, negative 2, and maybe 1/2 and 3/2. Okay. This will give us a sense of what is happening. If we have 1 over 2 minus 1, this is 1. 1 over 3 minus 1 is 1/2. 1 over 4 minus 1 is 1/3. 1 over 0 minus 1 is negative 1. This is negative 1/2, negative 1/3. If we plug in 1/2, we get 1 over 1/2 minus 1, which is 1 over negative 1/2, which is negative 2. Here we have 1 over 3/2 minus 1. 3/2 minus 1 is 1/2, so we have 1 over 1/2, which is positive 2. Okay, so these are some points. Let's now label these points on the graph. And I'm just going to go ahead and draw my vertical asymptote. Now let me do that with a different color here. So this again is, the graph is not, or this is the place where the denominator is 0, what we remove from the domain. Let's plot in these points here. So we have 2 and 1, 3 and 1/2. This is 1, 4 and 1/4. 4 and 1/3. And then we also have 1/2 here, so there's 3/2, which is 1 1/2, and that maps up to 2. So these are the points on the right side of the asymptote. On the other side, we have 1/2 here, mapping to minus 2, so negative 1, negative 2. We have 0, negative 1. We have negative 1, negative 1/2, so somewhere over here. We have negative 2, negative 1/3. And so you can see the following trends. And this asymptote always splits the graph. So you're not going to have a continuous flowing graph. The graph will be, continuous over here, and then you have to kind of remove your pen and then draw it separately on the other side of the asymptote. So graphs can never cross over asymptotes, right? Because these are not part of the domain. So graphs never cross vertical asymptotes. Okay, so we have something like this on this side, and then notice here that these graphs are getting closer and closer to the x-axis. So the x-axis is your horizontal asymptote. So horizontal asymptote, HA for short, is the x-axis, or where y is equal to 0. And that's the whole graph. That's everything that we wanted to do for this problem. Okay, let's go to a different one last kind of graph that we're going to see here. And this is going to be what's called a piecewise function. So what is a piecewise function? Let me just give an example of one. And we'll just graph it, because that's how you'll see that it's a piecewise thing. So let's say when x is less than or equal to 1, f of x is x squared. And when x is greater than 1, we have 2x plus 1. So what does this mean? This means that, so let's start with 2 parts. Let's evaluate f of -1, f of 0, f of 1, f of 2, and f of 3. And then we'll do the graph. So what is f of 1 here? Or -1, well, -1 is less than 1. So we're in this category, I'll call it category A, this is category B. So this is category A because -1 is less than 1, so we're going to plug in -1 here. So this is actually -1 squared, because we have to plug it into this part. Because the x value, -1, satisfies the fact that x is actually less than 1. So this is 1. F of 0, 0 is always also less than 1. So we plug in 0 here. We get 0 squared, which is 0. 1 is less than or equal to 1. 1 equals 1. So we also plug that in here. What about for 2? Well, 2 is bigger than 1. So 2 satisfies category B. So I plug in, I get 2 times 2 plus 1, which is 4 plus 1, which is 5. 3 is also bigger than 1, so we get 2 times 3 plus 1. When we plug it in, 6 plus 1 is 7. So what does this graph actually look like now? So now let's graph. So let's draw an xy plane here. Here's x, here's y. So I have 1, 0, -1. Let's just put in -2 here as well. 1, and then 2 and 3. Okay, so let's just plot these points for now. At 1, we're at 1. At 0, we're at 0. At -1, we're at 1. At -2, we'd be at x squared, which is 4, right? -2 squared is 4. So essentially, up till the point up till this is where x equals 1, right? X equals 1 is kind of the dividing point between the pieces of this function. So this is, think of it as one piece of the function. This is another piece of the function. So effectively, if we just drew the full graph of x squared, we just draw the full graph, but then we stop when x equals 1. And then we say, okay, what is the graph of 2x plus 1 looks like? Let me draw that with a different color. Well, at 2, we're at 5 here. So it's at 5. At 3, we're at 7. So it's a little bit higher here, somewhere here. Now, we know that the graph of 2x plus 1, that's a line. That's going to be a line going through like this, right? Well, do we just stop here? Not quite, because there's still numbers between 1 and 2, right? You could plug in like 3 halves. So for example, I could have had 3 halves here. And that would be, 3 halves is still bigger than 1. Well, 2 times 3 halves, we'd have 2 times 3 halves plus 1, which is 3 plus 1, which is 4. So at 3 halves here, we would be at 4. So we would continue the line. So my graph is not to scale. And what I do is, so if I was going to plug in 1, right? If I plugged in 1, I would get 2 plus 1, which is 3. I would have a point here, right? 1 comma 3. If I plugged in 1, so if I plugged in 1 in here, x equals 1 in here, I would have got y equals 3. But what I do is I say, okay, let me just leave a little open hole there, because that's kind of the starting point of the graph, of the rest of the graph. We just don't include that particular point. We include everything beyond that. Right? So this opening, what does this indicate? This opening indicates that this piece of the graph starts at 1, 3, and then the rest of the graph is what I want. I just don't want that one single point. I want everything else. And the way we indicate that is this little opening. So this, I don't know if I have another color here, but this indicates that the point 1, 3 is not part of the graph. However, everything else is part of the graph. Okay? So this is the overall graph of the function, where the red piece corresponds to this first part, or sorry, the second part, and the black piece corresponds to the x squared portion. Okay. So let me leave you with one exercise to try to graph another piecewise function. And we'll start with that in the next video. So exercise. So go ahead and graph the following. F of x equals x cubed plus 1 when x is less than or equal to 2. And f of x is negative 2x when x is greater than 2. Okay, so it'll be a similar procedure as what I did. The dividing point here will be at x equals 2, and that'll be the place where the graph splits. Okay.